Of course, no problem.
Okay, so welcome everyone for our Institute for Quantum Studies seminar this week. We're very happy to have Iosif Bena visiting us from Paris, and he's spending time at the KITP in Santa Barbara for a program there and has graciously agreed to come down and speak about his research. So Iosif was raised and educated in Romania, and then he came to the United States to study at MIT in Boston. And then he went on to do his PhD at University of California, Santa Barbara. And that's where I met Iosif. That's right. So we were classmates together at the time. And he was a student of Joe Polchinski working on string theory. And then he went on after that to do a postdoc at UCLA, and then was eventually hired in Paris, in Saclay, where he holds a position at the CEA. And he's going to tell us today about his research. Iosif is an expert in string theory. He's been working a lot now on the applications of string theory to problems in cosmology, and particularly to black holes. So we'll hear about some of the work on the black hole information paradox and some of his resolutions of that problem. So Iosif, we're very happy to welcome you. The floor is yours.
Thanks a lot for the invitation. It's very nice to be here. It's a beautiful place, and I know it's so good to meet you again. So this is work which has been going on in our lab for many years. The title is Physics at the Horizon. Mind the cap or mind the gap. It's up to you. I'm using a font which is not very precise, and they're both a cap and the gap. And I'll explain why. Why do we do black holes? Black holes exist in nature. We measure them. We see them in the core of M87 galaxy with the Event Horizon Telescope. We see them in binary systems. There's one at the center of the Milky Way. They're quite big. The one at the core of M87 is about almost 6 billion solar masses. The one in the Milky Way is 4 million solar masses. It's closer, but it's much smaller. And basically, and also they emit gravitational waves, which nowadays are measured. And they cause a great conflict. If you think about quantum mechanics and general relativity, they cause a great conflict between them. Why is that? In Einstein's relativity, black holes are produced by gravitational collapse. And they have a singularity in the middle, and they have a horizon. And everything, including light, which crosses the horizon, can never get out. And moreover, the horizon cannot hold stuff. Essentially, whatever you throw in the black hole, there's no memory of the stuff which formed the black hole. And the only characteristics, the information you throw into the black hole is, again, officially lost according to general relativity. The only characteristics of a black hole are the mass, angular momentum, and charge. 3 things. And if you try to build something like a black hole with extra hair and extra objects, you cannot. And there are theorems showing that you cannot. There are mathematicians going and proving those theorems. There are people working to establish that this is impossible in Einstein's general relativity. And it's impossible to distinguish between black holes which are formed by collapsing, regardless what you put there, matter, antimatter, elephants. I put administrators, and you told me that you have very nice administrators here. So, this is a colloquium which is used for other places. And I heard here, I heard good things about administration here. So, but, normally I put in French, I say, service de personnel, personnel office. Those are the guys which are poisoning our lives. Anyway, it's recorded. I'm willing to go on record. So, anyway, so the Schwarzschild black hole, all of you who took some sort of general relativity classes, there's a metric, there's a time component of the metric, there's a radial component of the metric. There's a place called horizon where this quantity goes to 0, and this quantity goes to 0. Looks a bit ugly, the physics, but you can actually do something called the Penrose diagram, which is some conformal mapping of this geometry, which keeps the light rays fixed. And for example, so the light, again, this is time and this is light. And you can take this metric and you can do some transformations to actually transform it into a metric describing this particular thing. So our universe is here. It's a conformal scaling. So the interior of the black hole could be 1 cubic kilometer and blows up to look the same as the rest of the universe. But this conformal scaling preserves the light rays. So essentially time goes up, space is here, and basically things time-like things just go in, and if something falls into the black hole, crosses the horizon, can never go back. Going outside of the horizon is really the same as going faster than the speed of light, going in a space-like direction. And again, this is impossible. So this is Einstein's theory, and again we have this beautiful black holes. This is the Schwarzschild black hole found many more than 100 years ago. In quantum mechanics, I'm not going to talk about this here. There's a wave function. The wave function is unitary. There's a Hamiltonian, which is Hermitian, and information is never lost. Everything we do in quantum mechanics, we can bring it back. So in quantum mechanics, you never lose information. In black hole physics, GR appears to lose information, at least in these black holes. And you can actually do a bit more quantum mechanics. You can do some, you can actually do some pair creation calculations near the horizon of the black hole. This is done by Hawking and also by Bekenstein. And they show that to black holes, you can associate a temperature and an entropy. The entropy of the black hole is just given by their area in Planck units. For the 4D black hole, it's given by area in Planck units. L Planck is very small, 10 to the minus 35 meters, you know about that. So, the area, is pretty big. So, then these entropies can be super mega big. And the temperature, it's a nice formula. For a solar mass black hole, it's, 10 to the minus 8 Kelvin. But this formula, I saw somebody giving a talk, this is really a formula which contains everything. This is quantum mechanics, h bar, it contains c, this is the speed of light. It contains G Newton, which is gravity. It contains K Boltzmann, which means that you have thermodynamics, and it contains 8 pi. It means you have circles. So you have all the ingredients there, and it's inverse to the mass of the black hole. And again, it can be very small for a solar mass black hole. It's 6 times 10 to the minus 8 Kelvin. Smaller black holes are hotter. Very strange. Normally, you think big things. Black holes are really the other way. The smaller they are, the hotter they are. And if you look at the random solar mass black hole, if you just calculate entropy, you get 10 to the 77 for a solar mass black hole, 10 to the 90 for the Milky Way guy, 10 to the 96 for the M87 one, which is here in the Event Horizon Telescope. And the biggest beast out there in the universe, which has been known so far, is the black hole in the TON 618 quasar, 10 to the 98 entropy. TON is not, everybody thinks about the ton, but it's not ton. It's like, Tijuana Observatorio something nacional, or, it's some Chile, I think it's either Chile or Mexico. It's some place which, really found a big thing, and, they call it after their observatory. So this is, TON comes from some physical place. And moreover, you can show that the physics of black hole is thermodynamic, meaning they obey the first law of thermodynamics. They obey the second law. If you coalesce to black holes, entropy only increases. So they really behave thermodynamically, and they have this super mega big entropy. And then if you just go back to 19th century physics, Boltzmann, you say great. Black hole, let's take the biggest, fattest guy out there, 10 to the 98 entropy. Therefore, the bloody guy has 10 e to the 10 to the 98 states. That's a lot of states. That's e to the 10 to the 98 states. That's a huge amount of states. And on the other hand, Einstein's theory, general relativity, says black holes have no hair. So for a given mass charge and angular momentum, in quantum mechanics you have e to the 10 to the 98 states, and in general relativity you have one big fast state. And this is really the biggest number unexplained in physics. Everybody says, oh, the cosmological constant. This is really the biggest number, number-wise, which is unexplained in physics. And it's really coming, it's a very fundamental number. I mean, again, the entropy of the black hole depends on all physics, the general relativity. It's really something which, is clashing these theories. And then, of course, you can do, out of this, when you have such a big discrepancy, you can formulate various paradoxes, like an information paradox. You throw something into the black hole evaporates, information is lost, quantum mechanics is violated. You can really do a lot of stuff. But this is really the root of everything. The fact that, quantum mechanics predicts, e to the 10 to the 98, GR predicts, 1, and, then, you take it from there. Now, the question is, since, Andrew's from Texas, I want to use some southern slang for, where is the black hole states, and how do they look? And the question is, okay, how can I solve this paradox? How can I, take a shot at, solving this paradox? There's a nice calculation done in string theory, which is, all quantum theory of gravity, perhaps the most advanced ones, perhaps the only one, depends on whom you ask and so on. I'm not going to get into these things. Now, string theory is a quantum theory of gravity. So, it's a theory which could explain this discrepancy because it has quantum mechanics, it has gravity. It should give you some framework to explain this. Now, string theory is a theory which lives in 10 dimensions, doesn't live in 4 dimensions. Tough luck. It has strings, it has membranes, 1D membrane, 2D membranes, 3D membranes, 4D membranes, 6D membranes, quite a messy business. And if you put D branes together, you can actually get charges which correspond to lots of black holes. You can just build black holes in string theory. You can put, D branes together in certain ways, and you can really get, lots and lots and lots of black holes. Now, there's a very beautiful work which was done by Stroman back in '96, and 3,000 other articles which followed through, which is the following. Let's take some strings and branes which have the same charge as a black hole. Turn off gravity, the same charge and the same number of particles. Turn off gravity, make gravity weak. Then the whole system is described using string theory, a bunch of strings and branes at zero gravity. And then you turn on gravity, make gravity strong. These things back react. They basically, they have a complicated dynamics. Gravity becomes strong, and you get the black hole on the other side, that's finite gravity, and you have the entropy of the black hole. And I can show you. I mean, I'll show you briefly how this works using these strings and branes. There's a very simple system which is called the D1, D5 P system. There are some D1 branes which are just some strings, some D5 branes which are some strings which are all some torus, but you can think about this for this as also strings. As some but those things are not quantum string. I mean, they're basically solitonic objects. You can treat them as heavy solitonic objects in this issue of parameters, and you can wrap them on a circle of radius r. Just if you put one D1 brane at a circle, there's a circle of length 2 pi r, and you have momentum quanta. You put a string here. This red thing is a fundamental string which has one leg on the brane and the other leg on the brane, which carries momentum. But the momentum is quanta as if you put one string, if you put one D1 brane on a circle of length 2 pi r, the momentum is quantized in units of 1 over r. I'm ignoring h bar. I'm a string theorist, so h bar is on. Now, if you put n D1 branes, instead of putting one D1 brane, you can put n of them. And you can say, great, let's put n of them. I can put them in many ways. I can either put them independently without joining them, but I could also join them if I want. So I can join them into some configuration where you have a single brane wrapping the circle n times and coming back to itself. Those things have the same charge, so they can go from one to the other. And I'm looking for the maximal entropy for a given charge. So, this has more entropy. I'll explain you why. So when you have one D1 brane of length 2 pi n1 r, the momentum is not quantized anymore in units of 1 over r, but in units of 1 over n1 times r. So essentially, because this string is wrapping many, many times and then coming back to itself, the quantization momentum changes, the momentum gap becomes much lower. Then you bring the D5 branes, which are again some other objects, and you also wrap them into a single object. So again, these blue guys are the D5 branes, you wrap them into a single object, and then you consider strings which are stretched from one D5 to one D1. These D branes are places where the strings can end, so you can have a string ending on one and ending on the other one. And then you can ask what's the mass gap of this configuration. And if n1 and n5 are co-prime, then the poor string has to go around n1 times around the first guy, and n1 time around again. It needs to go all the way. If n1 and n5 are co-prime, it needs to go n1 and 5 times around this thing before it comes back to itself. So the momentum quanta are no longer 1 over r or 1 over n1 times r, but they are 1 over n1 times n5 times r. Now, this is a pretty small number. I mean, if you take some random black hole and you want to express some compactification of string theory and you want to express the mass of the black hole in terms of the d brane masses and so on, this is a very, very small number. This is really a number which is very, very, very small. It's one over some. I mean, it's really over the h bar squared in some. I mean, it's really like a huge in some natural units. It's really a very, very small number. Now, how do you get the entropy of the black hole? You put the momentum, which is basically np unit of momenta. So there are np. So the momentum is equal to npr or np over r carried by quanta, which are basically of size 1 over n1 and 5. And you can ask how many quanta do I have? How many ways of carrying momentum do I have? You have n1 and 5 np total quanta. And the number of states is essentially how many ways can you get n1 and np? How many ways can you partition n1 and 5 np into discrete integers, which don't. So if n1 and 5 np is equal to 2, then you can have 1 1 or 2. If n1 and 5 np is equal to 5, then you can have 1 1 1 1 1 1 1 2 1 1 1 3 and so on and so forth. This is a mathematical problem. Probably give it to grad students, advanced undergrads or grad students. How many ways can you partition a number? You have. You can have some partition functions. Long story short, the calculation is you have e to the s partitions, and s is of order 2 pi times n1 and 5 np over 6. Those of you who know conformal field theories, there's a Carty formula. So there's a CFT of central charge n1 and 5, and np is the number of carriers. It's L0. So then there's a Carty formula square root of C times L0 over 6, which is the entropy of the CFT at high in the Carty regime. And this is also giving you the same result. So if you can also express this number in 1 plus 1 CFT language, but again, this is much easier to follow like that. Now, you don't only have one kind of string, because you have basically strings. These strings correspond. There are many polarizations of the string, so there are actually 4 bosonic polarizations, which are basically bosonic types of quanta. There are 4 types of. So essentially, you don't have to count partitions of n1 and 5 and p into black numbers. You can also put blue numbers, which are distinct, and green numbers and red numbers. You can have 4 kinds of numbers. So then you have more partitions, and then you also have fermionic partners, which you can either color blue or black. But there are only 2 kinds. So then you can count a bit more, and it's a rather straightforward mathematical exercise to show that the fermionic partners give you an extra. For every fermionic partner, you get a factor of 1/2 in this entropy, and for every bosonic factor, you get a factor of 1. And the whole calculation at the end is 2 pi times n1 and 5 np to the 1/2. So the 6, you have 4 bosonic carriers, 2 fermionic and they give you the 6 in this entropy formula. And that's how you get, so you get this nice microscopic calculation. Again, I'm doing strings and branes, zero gravity, no back reaction, just, some objects, stretching. They're not interacting at all. I turn off interaction and I just calculate how many states I have. You can also build the black hole solution in supergravity. It's a complicated solution. It has some harmonic functions, Z0, Z5, Zp to the 1/2 and so on. You compute the horizon area, and there's a horizon at r equals to 0 in these coordinates, and the area divided by Planck units, and it comes to be exactly 2 pi times the 1 and 5 NP. And when people did that, it was quite a nice realization that you count strings and branes in some weird regime of parameters, and you get exactly the Bekenstein-Hawking entropy. So we kind of know that the degrees of freedom of the black hole are there. They are there. They are somewhere in some corner of the theory. I can visualize them. And if you do more complicated black holes, this becomes, these things can become hypergeometric functions. So you're not matching, one number and a number, like a formula and a formula. You're matching really hypergeometric functions with hypergeometric functions. You're matching an infinite number of parameters from both sides. So, this is really, it's an amazing, it's a modular forms, mock modular forms again. Mathematicians galore. I mean, you have people who are just, in this field who are doing these calculations, who are just deep into mathematics, they're not talking to any physicists, they just work with mathematicians with Zagier, modular forms and mock modular forms, horrible. I mean, you can do, as much math as you want. I mean, if you want to pump math here, you do it. I'm not a mathematician, so, but there are some people who are really love it. And again, there are two different calculations. One of them is a Cardi formula in some quantum theory. So one of them is really, and the other one is a classical area. And again, you're matching functions. So there's an infinite number of numbers. I mean, you're not matching, 5 and 5. You're matching really an infinite series of numbers with an infinite series of numbers, and they all work out. And again, there's nothing like that in any other theory. So everybody says, oh, my theory of quantum gravity is doing this. Come on, I mean, there's nothing comparable. I mean, we have, we're matching infinite series of numbers, and those guys are maybe matching one number and with fudging one parameter. That's loop quantum gravity has one parameter which they fudge, and they match one number. So that's basically zero matching power. Again, there's another way to understand it. Many of you heard about this ADS-CFT correspondence. There's a correspondence between quantum gravity in some asymptotically anti-de Sitter space, which is some sort of bulk, and there's a boundary where you have some CFT. So this CFT, there are some states in the CFT, and they form an ensemble, and there's an entropy of this ensemble, and the entropy matches the entropy of the black hole. So this is the ADS-CFT correspondence. That's how you get. That's how there's another way to think about this matching in this language. So great, we can match the black hole entropy. This has been the state of the field in 96, 97, and so on and so forth. Everything is very hunky-dory. We got the entropy. But then you can ask more refined questions. Great, I have the entropy. What about a single microstate? What about one particular microstate? What about 17 quanta in in one harmonic and 25 quanta in some other harmonic? One guy. Let's take one guy out of this e to the 10 to the 90 states, and let's see what's happening to this particular guy when you go to strong coupling, when you go to the black hole regime. And for a long time, following, work by Satsky, Horowitz-Polchinski, and then, Chen Maldassen and Witten more recently. So those are the big shots of string theory. There's a standard law that, when you increase gravity, these strings and branes, gravity is an attractive force. Everything becomes smaller. The black hole horizon grows. At some point, there's a correspondence between the two things. And in the regime of parameters on gravity, it's finite to recover the standard black hole. So you have all these microstates, and all of them look like a black hole. However, over the past, again, 20 years, gosh, I'm old. Over the past 20 years, we've been showing that some of these microstates, some of these Stromer-Jabach microstates, when they go to the regime of parameters where gravity is strong, they don't have any intention to look like a black hole. Rather, they look like some geometries which have the same asymptotics as the black hole, the same throat, so they look very similar, but they don't have a horizon. They actually have some sort of smooth cap. And the horizon eats up information. The smooth cap, you throw something in, it goes out. So it's a very different behavior, from a scattering perspective. And the question is, given that we found a huge amount of those, the question is, are all the black hole microstates somehow maybe becoming geometries like that? Is it possible that, maybe this green arrow is what's happening to everybody, and this black arrow is some sort of, approximate description of the physics, but, the microscopic description is given by this big arrow. This is the big question. And again, this was posed by Samir Mathur, who was at MIT, and he's a professor in Ohio now at 2003. Is the black hole some sort of a statistical description of a huge number of horizontal geometries? You could say, and there are some arguments again, both by Mathur and also by firewall people, Al-Hiri, Marov, Polchinski, and Sally, that this fuzzball firewall idea is the only way to solve the information paradox. If you want to solve the information paradox, the only way to do it is to actually put something at the horizon to replace the black hole horizon by this kind of some structure of some sort, any sort. And again, those are quantum information theory arguments. So again, they're agnostic about string theory or anything else. They're just saying, if you want the information, and if you want to avoid quantum hopping, and there are some arguments which are just saying, okay, there's a one-way gate. if you want to get the information to get out, this is entangled to this, and this is entangled to this, and you must have something at the horizon which is not vacuum. It's a very simple argument, which Matur made first, and then it was the other guys, they extended to even more to a bigger setting. There are some other options. String theories nowadays, there's a common thing which you hear probably read in physics today, this quantum magazine. There's something called ions, or ER equals EPR, and they transmit the information out of a black hole by some non-local quantum effects. There are some wormholes which are essentially instantaneously transmitting the information. Again, I'm getting old, and there's a joke in people said, if you're not a left wing when you're young, you don't have no heart, and if you're not the right wing guy when you're old, you have no brains. This is a Romanian joke. I'm sure many people in the US don't appreciate it, but I'm getting conservative with and when I was young, this is a revolutionary idea. You replace the black hole all the way to the horizon, and this is revolutionary. Now people are saying no, they're like these islands, and this quantum effect which extend over some quantum non-locality, which extend over some distances, and the scale is m black hole cube. Now, m black hole cube in Planck units, if you take a solar mass black hole, this is 10 to the 80 meters, and that's 10 to the 53, the size of the solar universe. That's a bit too much quantum non-locality. I'm getting old. Young people, they love it. And in the US, there's a common. In Europe, not many people. I mean, in the US, usually there are fads. People work on them. They cool down, and then there are more fads. In Europe, people have a higher impedance. But people work on these things, and essentially this is one way to get the information out. You assume this huge amount of non-locality via some wormholes and via some and then you get the information out. So it can mathematically it's possible. Personally, I don't like it. 10 to the 53, the observable universe. I'm already doing enough non-locality to get the black hole destroyed. So anyway, that's H for me. There's another argument by Papadodimas and Raju, which is using some quantum arguments using state-dependent operators, which is not Copenhagen, but apparently that some people are saying you can still do, it's almost Copenhagen, you can do state-dependent operators, and you can observe, you can have some operators which are state-dependent, and they look like it looks okay. But again, those are some other arguments, and if you want, since people here are interested in these things, I can point to the papers. But again, I grew up in the old, I'm an old guy, so I'm on the Copenhagen side. There are some other formulations. One other formulation is that at the black hole horizon, thermodynamics effective field theory breaks down. You have new degrees of freedom kicking in. There's no space-time inside. You just have a huge amount of geometries, some quantum superposition thereof. And in ADS-CFT language, what we're saying is that the pure states, individual states, are given to horizonless configurations. The ensemble is given by the black hole. So somehow the black hole is really behaving as the thermodynamic description of this huge amount of solutions. And again, this is not some idea which people came up. It's something which you can really work out and prove by doing calculations in string theory. So this is not some hand waving thing. This is really something which is well established. If you want to do an ideal gas analogy, when you have the air in the room, you can describe it in two ways. You can either describe it in thermodynamics, ideal fluid, PV equals nRT. It's perfect for the heater. To get the heater to function, you don't need to know about molecules. If you want to do statistical physics and Schrödinger and so on, you need to know that the air in the room is not made of continuous fluid. It's really molecules. We'll zoom around, hit you back and forth. Some states are typical, like the one we're in. Some states are atypical. If all the molecules go in the corner or all die, in the newspapers, very atypical state. It can happen in the age of the universe, maybe, but so we really have a system. The microscopic interpretation is not at all thermodynamics. It's really a bunch of molecules. And if you want to do, for example, Brownian motion or Bose-Einstein condensation, you don't do continuous fluids. Brownian motion, the continuous fluid will never give you any Brownian motion. You need to look. You really need to understand the molecules. What we are saying is that the black hole solution, the one from the textbook, the one you read in textbooks, is really giving you the thermodynamic description. Far away, perfect at long scales. If you want to do gravitational lensing in astronomy, you don't care about all the microstats and so on. If you want to be far away from the black hole, it looks like a black hole, quacks like a black hole, you do your experiment. Even some things about LIGO gravity waves, are captured very well by this thing. But we are saying that if you want to do the information loss and if you want to do physics at the horizon, you really have to use these new microstate geometries, which is the real statistical description of the black hole. That's essentially what the philosophy of this thing is. So now, great, we are putting something at the horizon. Many people are. Ever since Hawking came up with his model of let's put something at the horizon and let's put let's replace the black hole by something to get the information out. everybody and their brother has been building, things, and this is the black hole, and like you had on the old cards, here these dragons, should be microstructure. So all these guys, which are trying to build black hole replacement, like graviton stars, quark stars, boson stars, mirrors. I mean, people are putting some mirrors on, and some they say there's some quantum black box or something, the quantum effects, some firewalls, bosons, and condensates of graviton. You hear all these ideas, they're nice ideas, people, it's good to try. But the problem is the horizon is not your normal vanilla place in the universe. The horizon is very weird, and black holes are very weird. Problem number one, if you build, so, let's say, you spend some time, you write some model, some theory with some, particles, and, you build some model which has the same mass as the black hole, which replaces the black hole at the scale of the horizon. If you do that, you have several problems. Problem number one is that, and there are actually 3 very stringent tests, and this is really coming from black hole physics, and it's quite non-trivial the way they're resolved. Problem number one is that this is the growth of G Newton. If you imagine again being God and dialing Newton's constant, make Newton's constant stronger or weaker, what would happen to the Earth if Newton's constant became stronger? We'd be crashing. If G became 10, 50, 100, flash, we'll be all crashing. The Earth would be like all problematic and so on. Maybe it will all go underwater. Very bad stuff. If you make Newton's constant lighter, things become bigger. Newton's constant, gravity is an attractive force. The stronger gravity is, the more it attracts things. The black hole horizon, on the other hand, doesn't do that. The black hole horizon grows. When Newton's constant is bigger, the black hole becomes bigger. The stronger gravity is, the bigger the horizon becomes. So if you want to replace the black hole horizon by some object, your object has to grow when gravity becomes stronger. Your object has to become bigger when gravity becomes bigger. And that's highly non-trivial. You cannot do it using like, particles or quarks or stuff. Anything, any normal matter in the universe, if you make gravity stronger, it shrinks. You need to have something very weird. And in string theory, you have these objects which are called d branes, which are some solitons. Their tension is given by 1 over G string. They are non-perturbative objects. And G string is G Newton in string theory is equal to G string squared. So you are emitting a string and absorbing a string. That's some, it's a pretty straightforward thing. So these objects, d branes of string theory, solitons, non-perturbative degrees of freedom, they actually become lighter when the coupling constant becomes bigger. They are solitonic objects. So again, so the soliton has a tension which is the inverse of the coupling constant. And so lesson number one. If you want to build a structure in the horizon, you must use non-perturbative degrees of freedom. You must use solitonic objects. You cannot just say, oh, I'll put something and replace the black hole. So there are some objects called boson stars and so on. Essentially, there's some toy models which work, but you need to have a field, and you need to replace the black hole. You need to adjust the mass of the field for every black hole. You need to change the fields, make them, change the mass of the fields. The string theory has these degrees of freedom, and in a sense, the mass of these fields in string theory, the mass of these degrees of freedom becomes lighter when the black hole becomes big and when gravity becomes strong. So it's really, string theory has some very funny degrees of freedom which allows you to have this behavior. This is problem number one. Problem number two, you need to have a mechanism not to fall into the black hole. Why is that? So this is the Penrose diagram. Again, this is the black hole. There's the singularity. This is a non-extremal black hole. I took it, it's a bit easier. This is called something called the inner horizon, outer horizon. And you want to build some structure. You want to put something there. You want to replace the black hole by putting something there. The problem is this is a null line. This is something, to stay there, you need to go at the speed of light. And there's a GR dogma that, you should not put anything at the horizon. And the reason is very simple. It's a null surface. If you put a massive particle and you want to stay at a null surface, you need to go with the speed of light. Infinite mass, back reacts, and bad. If it's a massless particle, sure, solve the wave equation, more than welcome. The black hole is just going to eat it up, and it will disappear. So you cannot put normal matter at the horizon. You cannot carry degrees of freedom. People say, I'm putting some membranes and some spins and some quantum stuff. You cannot put anything there. It's a place where just get flushed in by the flow of time. I mean, you cannot stay there. The flow of time will just flush you into the black hole. There's nothing you can do to stop it. You cannot, like the way you cannot get it back in time. You cannot build something there. People say, I'm putting a firewall or something. I mean, there's no way. It doesn't work. Gravity will just flush you in. And essentially, you need to have something called the support mechanism. You need to have some sort of stiff object which has some non-trivial support mechanism. It's very complicated to get something which again doesn't get collapsed by, doesn't get crushed by gravity into the black hole. And again, lesson number two: if support mechanism you have not, go home. Have you not? Go home and find one. And this is something which I call the quantum coyote principle. Essentially, this movies with Willy Coyote, which runs in the desert after like the big bird, and then at some point, runs the top of the edge of the cliff. Then keeps on running. At some point, realizes, hey, there's gravity, and the guy looks down and like poof, starts falling. That's the kind of this is the kind of really gravity, just so then all of a sudden gravity starts acting. If you don't have, if you just put some black box or some mirror or like some firewall or something without a support mechanism, it will just fall in. Gravity will just pull you in. There's no way to stay. There's no way to stay at the horizon. So again, that's the kind of quantum gravity principle. Okay, that's problem number 2. Problem number 3, it's even worse. It was shown back in 1939 by Oppenheimer and Barbie that, sorry, Oppenheimer and Schneider, that when you have a collapsing shell, you form a horizon. So take some shell of matter, take some super mega big shell of matter, shell of dust, make it collapse, give it some speeds. And actually, I think this guy Schneider appears in the movie. So, it's one of the guys. I was watching the movie and like, oh, this is Schneider. This is the Schneider. So I think Oppenheimer was doing this, when he was in Berkeley before. And so you take a shell of dust, you collapse. Now, when you have a super mega big black hole like this TON 98 black hole, the curvature of the horizon of the black hole is of order, maybe like 10 times on the Earth. So people can accelerate to 10G. Okay, some very fast pilots. So nothing should happen. You shouldn't have quantum gravity appearing at 10G. So the curvature of the horizon is a very, very small thing. Gravity is supposed to be very, very happily discussed here. Again, there are no quantum effects. And then the idea is, okay, great. This guy is going to keep on collapsing. And at some point, it will keep on collapsing. At some point, it will approach the black hole, the black hole singularity, which is here. And at that point, of course, so when the shell, so this is the shell, the gray thing, it crosses here. Here, the curvature is 10G. Nice, beautiful, empty space. You can just fall behind this guy and just keep on drinking your coffee. Nothing happens. And then at some point again, this guy will go, will collapse, singularity, strongly curved, crazy quantum effects, and so on and so forth. And this will all happen here. But in the Penrose diagram, you see that the horizon is actually in the causal future of this place. So if you really want to build something at the horizon, it needs to be here. And somehow you need to convince these quantum effects, which go from this region, to go back in time and basically destroy your space-time, in the causal past, which is really, or like at the space separation, which for this TON 618 black hole is 180 hours. So you need some sort of strong coupling, and then you need some sort of quantum effects which really come in and destroy your space-time back in time. That's not very nice. And again, I don't want to have any quantum effects. I mean, again, quantum mechanics is nice, but I don't want anything from the future to go back and destroy the past. I mean, this should not be happening. And again, we're talking about 180 hours, and so that's illegal. Now, how do you do it in string theory? The way you do it, you realize that the black hole has a huge amount of microstates, and in particular, it has microstates without any horizon. And there are e to the s of them. Again, e to the 10 to the 90. So we're talking about the super mega big amount of microstates, which all have structure at the horizon. When you bring a shell, the shell can tunnel. This quantum tunneling. Now, quantum tunneling has a very small probability, but you can actually compute it. So first of all, it was estimated by Per Krauss at UCLA and Samir Mathur. It should be over e to the minus s, but they didn't have the number. They didn't have e to the minus s or minus 2s or minus s over 2. That's important for the quantum tunneling. If you mess up the exponent, you really screw up the thing. But then we did the calculation in some corner of string theory using some M2 branes, top bubbling into something and so on, and we found the coefficient to be exactly e to the minus s, to be exactly e to the minus s of the black hole, plus some coefficient, plus some tiny thing in front. So what's happening is that this shell, when it's collapsing, instead of doing Oppenheimer Schneider and forming a black hole and forming a horizon, because it goes in a region where there are so many available end states, it will just tunnel into them. It will just tunnel into them, and essentially it will populate this thing. And so essentially quantum GR and classical relativity breaks down here because of this enhanced quantum tunneling. And you need to have, so if you are to build something which has the same structure at the horizon, it needs to have a huge entropy also. You need to have the black hole entropy. You cannot build something at the horizon which is just one solution or 2 solutions or 10 solutions or 20 solutions. You need to build e to the 10 to the 90 solutions. You need to build a huge amount of structure at the horizon. It needs to have, the structure needs to have e to the s entropy. So again, that's the third lesson. The black hole entropy, the structure must have. And again, these rules out many things. Now, why does this happen? Well, there's a tiny probability, and there's a huge number of states. And the question is, why doesn't it happen more often? So, take my favorite Romanian character and, ask, okay, why can't I have this guy? And, by quantum effects, tunnel into, I don't know, something, chocolate. Chocolate has the same amount of protein and calcium and, bones and stuff. Why doesn't, a human being tunnel into chocolate? Why can't I tunnel into chocolate? The first answer is, it's a very small tunneling probability. Sure, 1 molecule of me going to 1 molecule of chocolate, very tiny probability. But it's not enough. That's not enough. You need two things. You need the entropy, the tiny probability of the tunneling, but you also need a small number of states. If chocolate had the entropy of black holes, if chocolate had the entropy of had a huge entropy, you tunnel into chocolate. The reason I don't tunnel into chocolate is not only because there's small probability, but also because the entropy of chocolate is not large enough. And for black holes, the entropy is large enough. The black holes are the only beast in the universe whose entropy is large enough. Again, solar mass black hole 10 to the 77 entropy. The whole observable universe in the stars is 10 to the 70. So a solar mass black hole, just the black hole, the mass of the sun has more entropy than all the visible matter in the universe. So the entropies we're talking are huge. And again, you don't. I mean, if you are tunneling into chocolate, you don't because again, it's a small probability, but it's also the chocolate itself has a small entropy. It's really the entropy of the chocolate which prevents you. And again, homework, there's some students here, estimate the entropy of 100 kilos of chocolate and the probability of 100 kilo human to tunnel into it. It's a short calculation. So it's not good enough to have a few fine-tuned examples. You need to have the full thing, and you really have to capture the full phase space. Again, there's like this example. You have some gas, and you have some phase space dynamics. There's dynamics where this gas goes into some corner. This is very atypical fine-tuned dynamics. So there's dynamics where this goes all over the phase space, fills up randomly. This thing is a typical microstate. You really have to get a huge amount of geometries, and you really have to get a huge phase space. And what we are saying is that when you have the shell collapsing, there's a classical black hole which looks like this, and essentially there's some atypical microstructure, and then you have typical microstates, huge number of them. So the structure at the horizon, again, I want to emphasize, it can only exist if it has the same entropy as the black hole. It cannot exist otherwise. It cannot be formed otherwise. Otherwise, you just form a vacuum, and then that's it. You cannot go back in time. Now, I'll give you some. So again, those are not good enough. You need to have really a huge amount of families of of such solutions. Now, how do you build these solutions? Well, we are string theories to use some d-branes, and the d-branes have a supergravity back reaction, and there's some supergravity solutions and so on. And we're able to build solutions which depend on an infinite number of parameters, but actually they're given by arbitrary functions of 3 variables. So you put f of x1, x2, and x3. There's like triple infinite number of parameters. The solution cohomogeneity is 5, so they depend on 5 variables. Most of the solutions, Schwarzschild black hole depends on 1 variable, just the radius. It took Kerr 50 years from Schwarzschild to find the first black hole which depends on 2 variables. That's cohomogeneity 2, found by Kerr back in '69. So it's about 50 years after Schwarzschild. And then people found a few more, but people at most have cohomogeneity 2. I mean, maybe cohomogeneity 3. Here we have cohomogeneity 5. We're using supersymmetry. We have a way to get this ansatz, under some control. And we really solve, we really have all the 3 properties. We want 2.5 rather, because the entropy is not good enough. But I'll tell you later what the problem is. So it's really cohomogeneity 5, and this object we call it the superstratum because we have some super tube which has arbitrary shape, and the superstratum has anything. And when you had the paper, we call it Habemus superstratum. We really had the full solution. So we're quite happy that we could get so many solutions out. I mean, nobody believes so many solutions exist, and I think since Einstein found his equation, this is the largest family of solutions ever constructed. I don't think anybody built more solutions, larger classes than those. I mean, they're just a bit hard, but doable. And moreover, they have some features of typical microstates. I told you that there's a mass gap when you count entropy. There's a mass gap which is 1 over n1 and 5. Those guys actually have a mass gap of 1 over n1 and 5 because of some redshift and so on. There's some effects. Now you can ask, great, where you have some solutions which have the same mass and charge as the black hole. They have a long throat, but they have no horizon. Where's the black hole charge? Well, what's the charge? The charge is the coupling to the gauge potential. Q times A0 in the Lagrangian. Now, these theories, they have a more complicated Lagrangian. There are supergravity theories in 5 dimensions or in 10 dimensions, in 11 dimensions. And in particular, there's a coupling in the Lagrangian code, which is of the form A wedge F. So there's a magnetic field in 5 dimensions. I'm just giving you the 5 example. It's a bit simpler than in 4. There's a magnetic form, the field flux, and there's another magnetic flux. And together, 2 magnetic fluxes via this coupling term can actually source an electric flux. So these solutions have bubbles, have topology, wrapped by fluxes. There are fluxes wrapping these cycles, and 2 magnetic fluxes wrapping the cycle and can actually act as a source for the electric charge. So they really have. So these solutions can have the black hole charge, even if there's no horizon, there's nothing. You just have magnetic fluxes. Where's the black hole mass? Well, the black hole, again, these objects have magnetic fluxes which have an energy. B squared, E squared. There's an energy in the flux. So there's an F12. Whereas the angular momentum, well, I told you have both electric and magnetic fluxes. There's a pointing vector, and there's an E cross B pointing vector, which is F01, F12, for example. This is the kind of you always have such coupling, so you have an angular momentum in the direction 2. And this is, this is universal to all the solutions. You really have, the charge coming from, fully. So it's a fully smooth solution, no horizon, but a non-trivial topology. There's a complicated topology of bubbles wrapped by fluxes in these things. And moreover, okay, I'm not going to go through this. I mean, if you compactify to 4 dimensions, this is a very weird matter, which only exists in string theory, but I'm not going to get into this. I want to just, impress you why the bubbles with fluxes don't collapse. Because if you think about, take a bubble, take a two sphere, put a flux on it. So, put, for example, some magnetic flux, integral of F2 equals to 4 pi times n. So you have some two sphere with a magnetic flux wrapping it. This is quantized. Unless this number is an integer, you get the Dirac. So you put this bubble, and you can write the magnetic field in a very simple form. And if the integral is to pi, you assume spherical symmetry, and you get F2 to be like n sin theta d theta d phi. Or in f sub theta phi, the indices of f are just n sin theta. So this, if you take this f, you integrate it over the sphere, you get a number. And when you have such a solution, you can, again, it's topology and flux. You don't have a metric yet. Then you can say, okay, let's look at the metric of the sphere. D theta theta is r squared. G phi phi is r squared sin squared theta. So the energy of the flux is given by f mu nu, or the particular components are like d theta theta is up, g phi phi with legs up, f theta phi, and this is over the n squared over r squared. So when you have a quantized flux on a sphere, if you make the sphere smaller, g theta theta and grr become smaller, but the g with legs up become larger, and the energy grows. So the sphere, the topological sphere, which has a non-trivial flux on it, has a stiffness which doesn't allow it to collapse into the black hole. The black hole, again, matter normally goes into the black hole, but these topological spheres with flux on them, they're actually stiff. They really have the structure, they have a support mechanism which prevents the collapse into the black hole. And it was shown by Gary Gibbons, who's a professor in Cambridge, and Nick Warner, my collaborator, that this is the only mechanism to prevent, in classical physics, to prevent collapse into the black hole. Anything else you should do, unless you have topology and fluxes, anything else you should do is going to collapse into the black hole. I'm not going to get into, there's some CFT arguments, but I'm not going to get into this. So somehow the story seems to be that, when you go from this, Strominger-Vafa black hole at zero string coupling, there are some intermediate steps, in between Strominger-Vafa and, what we are doing, there are some intermediate steps where you can calculate at intermediate coupling, but you really have the typical states of the system. They, the horizon, as you go from zero coupling, you turn on gravity, and the guys become bigger and bigger and bigger, and the horizon never forms, and you basically get, the states of this guy extend all the way to the states of this guy extend all the way to they become large, they become horizon sized. And you can say, okay, great. What's wrong with the black hole? I have a classical black hole, beautiful black hole, small g Newton. Why do you throw the black hole away? We are saying that the black hole doesn't correspond to anybody in the Hilbert space. We are saying that all the states of the Hilbert space are spanned by such objects. And the black hole, really, there are some effects from quantum effects from the singularity and this tunneling, which really destroy the black hole. Why is this happening? And okay, there's a similar story for non-supersymmetric black holes. I'm not going to get into that. Why do you destroy the horizon? What's wrong with the horizon? There's a low curvature of the horizon, and I'm telling you that you have some quantum effects which destroy the space-time. I have a beautiful space-time, low curvature, nice, beautiful, as beautiful. It gets in somehow quantum effects destroyed. Why is this happening? Well, there are some. The short answer, the intuitive answer is there are low mass degrees of freedom. When you have low mass degrees of freedom, by uncertainty principle, you have huge, they have a huge extent in, the low energy, there's a huge extent in time. So, there's delta E, delta T, or like delta P, delta X. So you can really have, because the mass gap is so small, they mess up physics on large distances. But moreover, and this is common in string theory. You have many examples in string theory where you have low mass degrees of freedom, which mess up some space-time or some macroscopic distance. But moreover, there are some solutions which, I have a throat, again, it's a smooth solution, no horizon. And they make the solution to be longer and longer and longer. Classical physics should be hunky-dory. Coupling constant small, quantum effects turned off, everything is hunky-dory. And yet, when I approach when this solution becomes longer and longer and longer, you can actually quantize the solutions, and you can show that quantum effects can actually destroy these regions. So how can quantum effects destroy, this region could be like, 10 megaparsecs cube of space-time. How can quantum effects destroy, do so much damage on classical solutions? The answer is there's something called phase space squeezing. When you have some uncertainty principle and you have some, delta P, delta X, which is very small, if you squeeze your state on some, so you have a phase space, if you squeeze your state by some, magnetic field or something in one direction, you can make quantum effects to become very large. So this is, some example, I took it from some paper by some experimentalists. So normally, you have, this is H bar, so, you have like, quantum fluctuations, which are very small. But if I squeeze my state a huge amount of time in one direction, the quantum fluctuation becomes super mega big. on the other direction. And in this particular state, this was shown by some people who did the quantization, that you really have this kind of effect. You really have these quantum effects which become important on long distances. They destroy classical regions of space-time. And the reason is you're doing this phase-space squeezing. That's again another nice effect which comes out of these geometries. So, and again, I told you we have low mass degrees of freedom, which. And this low mass degrees of freedom, they come, the mass is really, really low, and you basically basically mess up the physics on horizon scales. There's a nicer calculation that somehow when you have a black hole, the way to get most entropy and the way to get the degrees of freedom is to just imagine making brane anti-brane pairs. The way you make electron positron pairs out of nothing, you just make brane anti-brane pairs, and even if it costs you energy, you get so much entropy that the free energy is actually negative. You actually gain free energy. The energy you have to pay price in energy to make these guys, but there's so much super mega big entropy in these guys that E minus TS, when you have some temperature, E minus TS really goes down. So somehow you are basically making stuff which normally, again, you put one electron and one brane and one anti-brane, or one electron and one anti-electron, they just want to annihilate. The energy pulls them together, but because they get so much entropy by being separated, actually the system goes into these states. And moreover, the bigger the black hole, the smaller the mass cap and the larger the size. And that's how you get the black hole. And this matches the black hole horizon. I told you that the black hole horizon gets destroyed by these guys, which extend on large distances. The bigger the black hole it is, the more degrees of freedom you have, the more fractionation you get, the lower mass gap you get, and the bigger the region where you mess it up. So it really matches GR. It really matches the fact that the horizon grows with the mass. That's so essentially there are four approaches at this point that pure black hole states have no horizon. One of them is again firewall, Alice Bob, quantum information theory, entanglement. There's no strong subadditivity and arguments by Amps and Matur that you must have something. Then you could have a firewall, or you could sail through. That's another question. And then there are some generic ADS-CFT arguments using the generic ADS-CFT arguments. Those are also like some approach. I didn't get into this, which explains that the typical states have no spherical symmetry. The black hole has spherical symmetry, and therefore the typical states should not have. I mean, there's something which people call scars. They don't. There are scar states which are not respecting Eigenstate thermalization. These states which we are building, they really have no spherical symmetry. And there's one question whether there are enough of them to span the Hilbert space and so on. But those are generic questions, and those questions, they don't care about the theory. They don't care whether you're a string theory or just some quantum gravity, which 500 years from now maybe people will discover a new theory which is bigger and better than string theory. And in that theory, these arguments still go through. Those are semi-classical arguments which using quantum mechanics, very basic stuff. These arguments are going to go through. And I have no idea. Maybe the universe is explained by maybe there'll be quantum theory which there'll be a new theory of quantum gravity discovered 100 years from now, and that's those things should be there. And then in string theory, you can actually do some calculations. You can follow black hole microstates from strong coupling using some mechanism, and we're doing that right now. Or you can build lots of microstates. And again, this is what we are doing. You can build a huge amount of solutions, and the mechanism is bubbles. They really have bubbles. They really form. And moreover, if you solve the wave equation in a black hole solution, there's no. I mean, if you just solve the wave equation, the wave falls in. There's no gap. These solutions have a gap, so there's a non-trivial, physics, new physics coming from them. So great. I have a few questions. So now, this is more or less, the construction. The thing which kind of interests me, and, again, people here, people like Andrew have expertise in them. I have a bunch of classical solutions. Again, they are a basis for the Hilbert space. They are scars. They are solutions which don't respect Eigenstate thermalization. They have very non-trivial symmetries and so on and so forth. And if I look at the hard typical state, so again, I take these solutions, let's suppose I'm very successful. I build all the black hole microstates. I build all of them. They are smooth solutions. I built e to the 10 to the 90. Right now, the entropy of those is a bit smaller. So the black, I didn't tell you that. The black hole is square root of N1, N5, NP. And the number of our solutions is square root of N1, N5, and NP to the 1/4. We are still being, we still have super mega big numbers. More than entropy of the universe and so on, but we're not really at the black hole. We need another ingredient. We are doing right now. I didn't tell about this, and this is the more recent work we're doing. But I'm sure we have those guys. The question is then great. The typical state of the subject, you have a Hilbert space spanned by coherent states, which look like geometry, with some coefficients, C1, C2, C3, over e to the minus S. That's how much they have to be, because the state is normalized. The question is, and this state, again, dynamically, there's a tunneling from any of them to any other one of them, which is quite large. And they will also move. They also, each of them can also have a local phase space. The question is, how do you interact with such a beast? if I throw some light, for example, it will go into one, it will go into the other one, it will go into the other one. Then one of the microstates shines it out this way, the other one shines it out the other way. Quantum interference, maybe there's nothing coming out. I have no idea. But this is one of the questions which, I'd really like to have an answer. How do I interact with such a beast? How do I determine that, the Hilbert space is spanned by these scars or not? What are the kind of, is there any, then in particular, if people do experiments at some point on black holes, is there any signature that of the fact that, this Hilbert space is really spanned by these scars, or just the Gaussian thermalization and looks like a round solution, and you cannot observe this particular structure. And essentially, another way is like how can you observe these things? And idea again, there's a huge amount of degrees of freedom. They really have all these guys. There's a huge amount of degrees of freedom. In these guys. And okay, huge, and it's X, and maybe future president, but okay. And but the thing which is funny is that if you look at these bubbles and these very non-trivial configurations, they really have different Kerr multiples. They really have different multiple moments. And okay, people have built, my ex-student who is a professor in Ohio State, and my ex-postdoc who is in Johns Hopkins, a professor. They built these non-supersymmetric solutions. The ones I told you about are supersymmetric, but they're already very complicated. I could spend another 5 hours talking about the non-supersymmetric ones. It's a big field. But just to give you an idea how the physics is the same. The physics phenomena are the same. The question is, what's the intuition? When you have an object like that, and you don't have a classical black hole which has vacuum at the horizon, but you have this stringy, deep brainy things which are big and messy. Some people call those things fuzzballs or firewalls, depending on your community. When you spin these guys, there's a very different structure. You have multiples. So when you spin, for example, a ball of dust or liquid or a solid shell, you get various multiples. Essentially, when you spin, gravity, you can calculate, for example, what's the mass dipole, quadrupole, octopole. What's the mass distribution of this side? How much the guy pancakes? When you have a black hole, when you spin it, it can pancake. And some objects pancake very much, some objects don't pancake too much. It's essentially this tells you how much the object is pancake. I think Jim Hartle was the first guy who did. I saw it at this conference this last week in Santa Barbara. He's the first guy who asked these questions and how to calculate these things. Now the Kerr black hole is very weird because the Kerr black hole has vacuum at the horizon. So you are spinning something which is just vacuum, pure vacuum. So then the multiple structure is very, very strange. Essentially, the even mass multiples are finite and the odd ones are zero. So you really have finite, zero, finite, zero, finite, zero. Very strange signature. A random bunch of garbage, dust, liquid, solid shell, boson stars, whatever you spin, even our solutions. If you spin random garbage is going to be like, finite, some finite numbers. And the Kerr black hole has really finite, zero. So if you measure anything like, the mass quadruple, the mass octopole, for example, you really get, very, very strange, very strong constraints. The Kerr black hole must be zero. And if you measure anything above zero, or different from zero, then you have a signature that you don't have the Kerr black hole at the horizon. You don't have vacuum at the horizon. And we're doing them. There's things, there's some numerical solutions which I need to do, and people are actually measuring them. So there's like this. I don't know if I have a slide here. No, I don't. So people are there's like this new gravity wave observer called LISA, which is going to fly soon, and they'll measure extreme mass ratio in spirals where you have a small black hole and a big one, and they move around each other off the orbit plane. And they're able to constrain these things according to some people. You can get up to 8 or 9 multiple moments. So in principle, we'll have very strong things coming up if LISA, if we're alive until then. If LISA flies, we'll have very strong constraints on this thing. And we're basically saying that you should not have the Kerr structure is very special, and these microstates don't have that structure. But again, that's an argument of one microstate. But what's happening if you look at the quantum superposition of all d⁻⁴ of them? You get the same results. Can you quantum mechanically superpose guys? Maybe all of them have positive dipole, positive octopole. If you superpose all of them, you should still be positive. There are all these arguments, how to do with this big fat mess, which with a lot of tunneling, and how to get out of it macroscopic quantities, which we can fit to these things. So anyway, that's the situation. So to summarize, again, quantum unitarity arguments, just preserving quantum mechanics, you must have something in the horizon, which takes the physics out. Either you have non-local tunneling, the size of the universe, or you have some structure at the horizon, but the structure needs to be very, very, very weird. It needs to be non-perturbative. It needs to have enhanced quantum tunneling. Otherwise, it cannot stay there. And string theory, luckily for us, again, I didn't expect that honestly. 10 years ago, I started working in this field to kill this idea. And it just came out. It just came out. Essentially, all this new physics came out, and in particular, this enhanced quantum tunneling. It's really some calculations which we can do to see all this nice physics. And the intuition is, again, low mass modes. You put a lot of stuff. You create these brane and anti-brane pairs. Low mass modes, fractionation. Low mass modes, they mess up the space-time on a huge scale, and you just destroy space-time, and you get this new structure at huge horizon, the horizon scale. Habemus, have these papers that the biggest family of solutions ever built since Einstein, and the question is, okay, luckily with Lisa and with maybe even like Virgo, people are computing multiple moments. People are going to constrain those also. Like there's something called love numbers, which appear in the five post-Newtonian order. They're basically the way the black hole horizon. When you have two black holes, the way they tidally deform, and so multiple moments are you spin it, and then you see how it changes. Love numbers, you bring something else, and you see how they interact. For black holes, love numbers are 0. So again, that should be a big smoking gun. Anything you build is going to be non-zero. And people in LIGO work are paying attention. So right now, people are inviting us at conferences. I'm applying for a 10 million ERC grant with 4 nodes. Which goes all the way from string theory to feeding into LIGO and Lisa data pipeline. So in principle, it's something which people are doing, and people in the community which does LIGO Virgo data, they're very interested in building these things. Anyway, so that's the story. So luckily, it's coming within experimental reach. I don't know if it's our lifetime or not, but things are moving. Thank you.
Okay, thank you, Iosif. Questions, comments, discussion? Yes, Emily.
Yeah, thank you. So when you talked about the ability of string theory to match the calculations of the state space and the infinite series of numbers, attributed that success to ADS-CFT. So in my understanding was that ADS-CFT isn't sort of uniquely applicable to string theory, and you can put arbitrary gravity theories in the bulk. So I wonder, does that mean any gravity theory that's compatible with ADS-CFT would have the same success, or is there?
I think it would work. Because somehow at least for supersymmetric black holes, it would work, because in ADS-CFT is just saying you have some central charge, which is C, and you have some momentum numbers, which is L0, and there's a Cardy formula, which is square root of C times L0. So if you build the black hole in the bulk, which is dual to some excitations on top of it, and you apply. If ADS-CFT is correct and extends beyond string theory, which again nobody knows, but I hope it does. I hope it's a universal way of doing CFT calculations. That's my hope about ADS-CFT. So string theory helped discover it, but I think it's a universal feature, just a shorthand of doing CFT calculations at large central charge and large 0 and so on. If that happens, it's almost automatic. It's the Cardy formula, square root of C times L0, and in the CFT you count the entropy, and you have the Cardy entropy. In the bulk you have the black hole, and the things match.
Thank you.
So,
Okay, other questions? Tathagan.
Yeah, thanks for the nice talk. I was just wondering something about the chocolate argument you gave. So, we don't tunnel into chocolate because it's at a lower entropy, and I was wondering, why don't we tunnel into something with higher entropy?
the problem is the stuff with higher entropy doesn't live nearby. So when you collapse a shell of dust, there's a huge entropy. It's not enough for the entropy to be in the universe. I could tunnel into the Andromeda galaxy. The tunneling to go into the Andromeda galaxy, even if the Andromeda galaxy has a huge entropy, I don't tunnel into it because I have a huge distance to go. So my tunneling probability I get a factor of distance, which kills my e to the minus s. So I have an e to the minus s to tunnel if my size and the size of this chocolate is the same, more or less. So if I have chocolate, 100 kilos of chocolate, the same as me. So when I approach it, I can tunnel into it. If I'm 10 kilometers away, I get a much, I need to tunnel, I have a much longer barrier to tunnel through, and then I pay a much higher price. So in principle, you could have some guy out there with a super mega entropy, which nobody knows, and we could tunnel into it. The guy could be in the Andromeda galaxy and would have a huge entropy, and we could start tunneling into it right now for all that, but it doesn't happen somehow. In these setups and in these calculations, when you have a shell which is approaching which is approaching, in our calculation of this tunneling shell, essentially you have some branes, and when they're far away, they don't tunnel because you have a coefficient, you have an extra to the minus s from the distance, but when they approach the region of the black hole, then the tunneling becomes over the 1. So you need to have this huge entropy and this huge amount of degrees of freedom concentrated in some region which you approach. If they are far away, no, you don't care.
Other questions? So I had a question. You mentioned, so in your calculations, you're doing this in a particular model of string theory. So you have, first of all, you build the supersymmetry, then you have the strings, then you have the d-branes, and you have the multiple dimension of the d-branes, and then you have the topological d-branes on top of that.
Yep.
And each level is a further layer of abstraction that we don't have direct evidence for any of these things.
Indeed.
And so I guess I have two questions. One is, does that make you nervous you're getting farther and farther away from connection with provable reality? And the second question is coming back to Emily's question, to what extent do the conclusions you're drawing here generalize away from the particular models of string theory that you're calculating these things in?
No, so the point is, to get the universe in string theory, you need to compactify some horrible Calabi-Yau with some horrible topology and so on. We don't have, we cannot do our calculations except on very simple setups, thinking on a torus, and the universe is not on a torus. So we can do some calculations for some black holes in string theory, in some particular background which are easy to calculate. It's not easy, but still, but what's happening historically, and again, I'm counting on a dose of luck. There's something which happened in string theory about maybe almost 20 years ago. People are doing quantum chromodynamics in QCD. It's something called ADS-QCD. They're looking at quantum chromodynamics, and they found that the entropy versus viscosity ratio of quark gluon plasmas in string theory, in some string theory models, which much smaller than whatever anybody calculates in any other theory. And people take one model, you calculate, another model, you calculate. You take 1,500 models of quark gluon plasma in string theory, you calculate, it ends up to be 1/4 pi. And then people started measuring this low viscosity at the RIC in Brookhaven, and they found that the entropy of this quark gluon, the viscosity over entropy ratio was again about 1/10 plus experimental errors. So 1/4 pi, 1/10. So what we do in string theory, we count. We have all these models which mathematically they are consistent. They tell us that in this theory, the structure of the horizon has these properties. What I hope is that, for example, in all these theories, you'll get, for example, when you spin the black hole, you have the mass octopole, which is 0 in GR. What I hope is that it's going to be positive and with some fixed, in some range in all these calculations. So then I'll say, great, for black holes made all this, stringy, messy stuff. I have a prediction that string theory says the octopole moment is going to be over the 1/2 of the quadrupole divided by the mass of the black hole, something. And it's quite likely that it will stabilize in some range. It's very unlikely that when it will go all over the map. Maybe God is not good to us, and maybe it will go all over the map, and then we have no prediction. This can happen, but so far there are some circumstances, and in particular the ADS-QCD, where string theory predicted some number completely out of the hat using a horrible supersymmetric n equals 49 nothing to do with QCD, but somehow you have this universal dynamics happening at low energies, which is more or less captured by these models. Even if these models are using supersymmetry, it's a bit like condensed matter. In condensed matter, you're assuming delta function potentials and so on. You're looking at the block wave function. You don't have delta function potential. You have atoms and so on. But somehow the universal characteristics of a bunch of delta functions potentials captures well enough electrons and bands and conductivity and so on. You don't need to really calculate the 1/r potential of all the electron cloud. You might you can approximate the atoms with delta functions and you get the right answer. And that's a similar thing here. We have all these models of black holes which we build on Tora using d-branes and so on. If we get all the real world black holes which are neutral, but again we obtain them in some string theories to have some properties, and we find that these properties are very different from the Kerr black hole, and hopefully also they point in the same direction. The worst is if one black hole in string theory has quadrupole which is positive, octopole which is positive, the other one has a negative one, and you get a big distribution, then tough luck. But we have some objects called multiple ratios, which I believe they're going to be constrainable. So I have a PRL with my exposure now. He's a professor in Lover. So we have some objects which I believe are constrainable, and I believe they'll have some universality properties. But that's a hope. We first have to construct these guys, build a lot of them, find what's happening, find their properties, and if the properties cluster in one particular thing, then we'll have a smoking gun. So that's in a sense, and that's why, for example, for this super mega big ERC application with the experimentalist, we're not looking at one guy. If we only looked at multipoles, we'll be unlucky. But if you look at 20 of the objects, you can look at low numbers, you can look at like, some emission of, there are some numerical mergers and so on. We really have like, a lot of places where to look at. And if you find that, in string theory, like in all the models you have, they have the same property for one particular object, that's a smoking gun that, you have this structure. That's indeed but this is the approach. We don't, these guys, the guys who build right now are like, string theory on the torus, very, very far away from the real world.
Okay, let's thank Iosif again for the talk.